Hello, everybody. My name is Dragos Ilie. I'm an assistant professor at Blekinge Institute of Technology, located in the city of Karlskrona in Sweden. And on this slide, you can see a picture of our beautiful campus during a warm summer day. Today, I will be presenting a paper called On the Design and Performance of Chinese OSCCA-approved cryptographic algorithms. Before continuing, though, I would like to acknowledge my co-authors, Luis Berman Martin-Kauppi and Qiuping He. Many companies would like to expand on the Chinese market. If a company wants to establish itself in China, they need to follow Chinese law. Legislation concerning the use of cryptography is defined by the State Cryptography Administration, OSCCA. More specifically, commercial encryption is handled by the Office of State Commercial Cryptography Administration, OSCCA, which is managed by SCA. Until recently, China was regulating the import, export, sale, use, and research of commercial encryption based on legislation issued in 1999. These regulations prohibited foreign encryption products and required all companies or individuals selling or producing commercial encryption products to gain the OSCCA's approval. The algorithms above are commercial cryptographic algorithms that were mandated by the SCA to be used within China. Only these three algorithms at the top, marked in bold, are within the scope of the paper and of this presentation. In 2019, China has adopted the cryptography law, which regulates the use of encryption methods to protect data in transit and at rest. The law, which came into effect on January 1st, 2020, divides encryption into three different categories: core, ordinary, and commercial. Core and ordinary encryption are used for protecting China's state secrets at different classification levels. Commercial encryption is used to protect information that is not considered a state secret. The new law removes many restrictions from the 1999 regulations. In particular, it allows use of foreign commercial encryption products that have completed a certification process. The goal of this process is to verify that the products comply with Chinese national standards and regulations. Unfortunately, currently there is no clear definition of what technologies fall under commercial encryption. Also, the details of the certification process are not available yet. Thus, it may be easier for a company to modify their products for the Chinese market to use the OSCCA-approved encryption algorithms and thus remain compliant with Chinese law. The problem of such a company is that they do not know in advance how the replacing algorithms will affect the performance of their products. The replacement algorithms may increase response times, energy consumption, and memory utilization, which in turn may increase capital and operational expenses. Therefore, the aim of our study was to better understand the design of the Chinese OSCCA-approved algorithms, and also to be able to quantify the performance impact in terms of execution time and memory usage when replacing standard cryptographic algorithms with the Chinese counterparts. So we have focused on three different classes of cryptographic algorithms. We focused on digital signature algorithms, on hashing algorithms, and algorithms for symmetric block encryption. In the case of digital signatures, we have chosen to compare SM2, which is a Chinese algorithm, with ECDSA and RSA. All three of them, they are based on asymmetric encryption. ECDSA and SM2 make use of elliptic curve cryptography, ECC. In our study of digital signatures and their performance, we focus on three specific operations: key generation, signature production, and signature verification. We have also included RSA, although it is expected to perform worse than ECC-based algorithms. We did this for two reasons. The first one is that it provides a baseline from which to measure performance gains when using ECC. The second reason is that if we would find that ECC performance results are similar or even lower than those for RSA, this would be used as an indication that there may be implementation issues in the library we used to do our testing. For hashing algorithms, we've chosen to compare SM3 with SHA-156. Both algorithms use the Merkle-Damgård construction, that is the iterated hash function. SM3 uses a Davis-Meyer compression function, while SHA-256 uses a compression function similar to Davis-Meyer. The difference is that in SM3, an XOR operation is used, whereas in SHA-256, an add operation is used instead. For symmetric encryption, we have chosen to compare SM4 with AES-128. The reason being that AES is most likely the de facto standard in today's symmetric block encryption algorithms. Most modern Intel processors, they support something that's called the Intel Advanced Encryption Standard New Instructions, AES-NI instruction set. These instructions are designed to accelerate the performance of the AES algorithm by 3 to 10 times compared to complete software implementation. This type of acceleration is not available for SM4. However, there are scenarios, for example, in the case of embedded devices in an IoT settings, where other processors are used or processors from different vendors. In that case, AES cannot benefit from acceleration capabilities. Therefore, when comparing the performance of SM4 and AES-128, we look at both AES cases, that is with and without the extended instruction set that provides acceleration. We have run 3 experiments, and you can say that at the core of these experiments, there is a 1 GB file located on a RAM disk, and any temporary or output files are also placed on this RAM disk. And the reason we make use of RAM disk is to alleviate or even try to eliminate the effects of disk I/O on our measurement results. The 3 experiments, they match the 3 different classes of cryptographic algorithms that were mentioned before. In the case of experiment 3, which deals with symmetric encryption and decryption, we chose 3 different encryption modes. We have included electronic codebook ECB mode, although it's deemed to be unsafe. The reason for doing so is that we use that as the baseline to be able to judge performance improvements or performance decrease when the other 2 modes are being used. In this case, cipher blockchaining, CBC, and counter mode. To implement those experiments, we made use of 3 cryptographic libraries. Initially, we only planned to use OpenSSL and Botan. And the reason of using more than 1 cryptographic library was that in case there were any implementation issue, we hoped that by using multiple implementation, we'd be able to spot these problems. However, when we are designing the digital signature experiment, we noticed that the OpenSSL release at that time lacked a specific feature, and that's described in the paper. So the solution was to fall back on using GMSSL. And the difference is that initially the Chinese cryptographic algorithms, they were released in the GMSSL library, and then later they were ported to OpenSSL. To quantify performance, we have collected 4 performance metrics from the process that was executing the cryptographic algorithms under test. We have collected elapsed real time, CPU cycles, and the resident set size, RSS, which is the RAM size that is being used by the process. And these metrics were collected with standard Linux utilities that are also listed on this slide. The general results indicate that the real time is largely proportional to CPU time and CPU cycles. Most likely this is due to the use of the RAM disk, which alleviates the effects of disk I/O. We also seen that memory usage in all cases, it's in the range 4 to 5 megabytes. So in order to, due to time and space constraints, then the following graphs will only show results related to the real-time metric. Here we have digital signature results, and as you can see here, to the left we have the results for Botan, to the right we have results for GMSSL, and we see groups of 3 bars. Each bar in a group represents one of the algorithms that are being investigated. In this case, the orange bar represents RSA. And there are 3 groups. The first one, it shows results related to key generation, the second one to signature production, and the third one to signature verification. And similar for GMSSL. And it's important to keep in mind that signature production and signature verification also includes time for computing the SHA-256 digest for ECDSA and RSA, or the SM3 digest for SM2. What we can see from these graphs is that key generation and signing for RSA takes longer, and this is an expected result. However, here we can actually see the magnitude. Key generation for RSA requires more than 350 milliseconds, whereas key generation for SM2 and ECDSA, they take less than 1 millisecond. Now, these differences are not as large in the case of GMSSL, but still what we can say by looking at these figures is that SM2 and ECDSA show similar performance, both in BOTAN and GMSSL, and definitely RSA has much, much worse performance. Here we have the hashing results for BOTAN to the left, and this time for OpenSSL to the right. So what we're comparing here is how much real time it takes to hash a 1 gigabyte file, and we can see that it always takes longer time for SM3 to do the hashings than for SHA-256. In the case of OpenSSL, it actually takes twice as long for SM3 to produce these results. And our hypothesis is that OpenSSL, the sort of SM3 is a rather new addition, or was a rather new addition to OpenSSL when we were doing the study. However, SHA-256 was supported since 2010. So for SHA-256, developers had more times to focus on optimizing the performance of the algorithm. So we believe this could explain the difference that we are seeing. Finally, here we have the results for symmetric encryption. Again, we have groups of 3 here. To the left is BOTAN, to the right is OpenSSL, but the groups of 3 here represent, again, the algorithms that we are comparing. In green, we have AES-128 with acceleration capability. With gray we have vanilla AES, and blue, it's SM4. And at the bottom, we see the different modes of encryption and, of course, decryption. And the same organization applies to OpenSSL. So what we can see here is that SM4, it's much lower than AES-128, regardless of operational mode. And you can see these are SM4, it's a blue bars in these bar charts. Even without hardware acceleration, and then we're looking at the gray bars, AES is still faster than SM4. So one other thing that surprised us a little bit was that CBC mode outperformed the other modes for decryption only. We don't have a very good explanation for this. A possible explanation can be if that, for instance, the counter mode is not able to exploit the parallelism that is existing in our device. At least that's what the measurements indicate. So the aim was to sort of get a better understanding what happens if we are to replace standard algorithms with Chinese algorithms. And this table tries to make that visible in an easier way. All right, so the way you would interpret this is if you have a box which is colored green, it means that replacing standard algorithm with a Chinese algorithm would improve the performance. Whereas if you see red in a box here, it means that when we are replacing the standard algorithm with the Chinese counterpart, then the performance is worse. So what we can say here is that Chinese algorithms perform better or equally well for digital signature operations. Symmetric encryption operations are significantly worse, with performance hits in the range of 85% to 915%. It is acceptable. I don't know, I guess it depends on the application that it's using this cryptographic algorithms. But what we can say is that user experience tests will be required after migrating a software product to Chinese encryption algorithms in order to make sure that the customers will not be disappointed with the products using these algorithms. So thank you for listening, and I guess we'll meet in the Q&A section.